Hello everyone and welcome back. Now, in the previous two videos, I spent a lot of time introducing you to linear dynamical systems, especially in continuous time. So, the question is, was it useful? Right? Most equations that we see in nature are not linear, of course, right? They are very complicated. They have a complex interplay between variables, and they come in very nonlinear varieties. Well, I have great news. It turns out that all of the theory that we were doing for linear systems can be carried over in a very specific way to help us understand nonlinear systems. And let's actually start by thinking about a general nonlinear system, okay? So let's imagine I have, the derivative of x, which is a vector, which depends on time, is equal to a function of x, okay? So the first thing that we will make an assumption about is that we have an equilibrium. So equilibrium, or steady state if you'd like. So an equilibrium, x naught, which is the same as saying f of x naught is equal to 0. Remember, that's what it means to be a steady state. It tells us we don't change in time. Okay, well, then what we can do is we can look at what's called the Jacobian matrix. So we've seen this before when we looked at multidimensional Newton's method. So I'm going to denote it as df, d standing for a derivative. This is evaluated at the equilibrium point. It is a big, ugly, complicated matrix. It says take the first component of f1, or sorry, of the vector f, which I'm calling f1. Take the partial derivative with respect to the first component of x, I'll call it x1, and evaluate at the equilibrium. Similarly, do the same thing for the next variable. All right, so it's just a vector of gradients across the top. In this case, it's all of the possible gradients of the first component of f. And then you can repeat this with a vector of gradients all the way down to the last component of f. All right, so now I get this nice matrix of all the possible partial derivatives of f. So let's do this. Partial fn, partial xn, x naught. So this is just a matrix, right? It's written complicated. It's a big symbolic thing. But these are just numbers, right? They're partial derivatives evaluated at whatever the equilibrium point is that you found. Well, this is a matrix. What do we do with matrices? We find eigenvalues and eigenvectors, okay? So why is this thing interesting? Well, here's the basic idea. If I take x prime equal to f of x, let's do a little Taylor expansion, okay? Let's do a Taylor expansion of f around my equilibrium point. So here's the basic idea. Just like with Newton's method, I want to fixate myself to a region of space. So with Newton's method, you fixate around your guess. In my case, here, I'm going to fixate around the equilibrium point, okay? So I get f of x naught plus, now this is where the Jacobian comes in. I get the derivative at x naught times the difference in x to the equilibrium, and then a little more. Okay? Now, what do I know about this? Well, first of all, I know that this is an equilibrium point, so this piece disappears. So now, essentially, if I take a linear approximation of this function, I get a linear dynamical system, right? The derivative of something is equal to a matrix times its current state. If you'd like to write this in a nicer way, you can always notice that if you center yourself around x naught, this would give you y prime is approximately this matrix times y. That right there is a linear dynamical system. We've already seen this, right? We've seen that it's entirely determined by the eigenvalues and eigenvectors of the Jacobian matrix. So what is this saying? It's saying that if you zoom in close enough, right? That's what a Taylor expansion is doing. It's saying stick close to this point of interest, this equilibrium point, if you zoom in close enough, you're basically got a linear dynamical system, right? You can chop off all of the Taylor series terms beyond that thing. But with the linear dynamical systems, I can analyze it. And it turns out that the analysis of this linear system carries over to the original nonlinear system. But it only does so locally, just like with our optimization examples with the Newton's method. But in particular, we saw that if all the eigenvalues of this thing have negative real part, all of the solutions decay down to 0. Right? That came from the e to the a times t. If all of the a's are negative, everybody contracts down to 0. So in this case, we would say that x naught is stable if all eigenvalues of the Jacobian matrix have negative real part. Okay, so they can be complex if they want to be, but all I care about is if they have a negative real part. And this implies that x of t goes to x naught when we start close to x naught. Okay, so what this says is that if your initial condition starts close enough to that equilibrium and it's stable, you're going to get sucked into it like a bed of quicksand. Okay? I'm being purposely vague here and not telling you how close you have to start. And this is not because I am trying to hide something from you. It's because there's a lot of times no definite answer. Right? It is a system-dependent problem to figure out how close you have to be. Right? It depends on what the specific f of x is and how complicated it is, just like we saw with multidimensional Newton's method. And even whenever I give you a specific right-hand side, it's not obvious. It's still a very difficult task to figure out how close you have to be. But this is important. This gives you a robustness of your potential equilibrium point. So if you think back to the tree example that we cared about, where we want to know if there was a coexistence equilibrium point, what we can see here is that if that coexistence equilibrium point was stable, then we don't have to be exactly on it. We could set up our system so that we're close to it, right? It affords us a little bit of wiggle room, and eventually we sort of contract into and fall into that coexistence state. Okay, so actually, let's go ahead and do that. Let's actually look at the tree system again, okay? So I am going to go back to that example on the trees that we used in the video on steady state analysis. And I'm going to make some assumptions, okay? So I'm going to put some actual numbers into this thing. So the first thing I'm going to assume is that the hardwoods grow at a rate of 10% per year, and the softwoods at a rate of 25% per year. So this is very, very similar to what we did with the whale problem. Okay, so now we know these growth rates. And we know that an acre of forest land can support about 10,000 tons of hardwood and 6,000 tons of softwood. Those are our carrying capacities. Okay, we don't know exactly what the equilibrium state is going, or sorry, what the extent of competition is, but let's make a little assumption, okay? So let me actually just write down my differential equations. Remember, I have the derivative, or the rate of change in the hardwood biomass. Now, again, let's put in some values. I have a 10% growth rate, 0.1 h, 10%. And then I have 0.1 over the carrying capacity, 10,000 h squared. And then I have that competition term, B1. Remember, it was B1 h times s. Now, here's what I'm going to do. I'm going to make our lives a little simpler. I'm going to assume that B1 and B2 are equal to a half of A1 and A2. Remember, this was A1 right here. So in my case, this becomes 0.05 10,000 HS. And similarly, for the softwoods, I get 0.25, 25% growth rate times S, minus growth rate divided by carrying capacity. Sorry, this one was 6,000, pardon me. 6,000. S squared. And then, again, I'm going to assume the competition is half of this A1 value. So this is 0.125 over 6,000 HS. Okay, so just so that we're completely aware, we've assumed that the competition is, so B1 is equal to A1 over 2, and B2 is equal to A2 over 2, okay? So you might have to refresh yourself with some of these variables if you are following along. If you go back to that steady state lecture and fill in the gaps, right? R1, R2, A1, A2, B1, B2. I made an assumption that's going to make my life, at least achievable. Again, remember what mattered was that A1 was bigger than B1 and A2 was bigger than B2. Remember, this was one of the critical components to determining if we had a steady state or not. Okay, so in this case, we can actually compute the equilibrium value, right? The coexistence state that we cared about. Here's my equilibrium. I'm going to call it H naught and S naught. In this case, my H naught is about 9333. You can just take all of these A1s, B1s, R1s, and so on and so forth, and put them into the formula that I gave you when we did this problem the first time. The other one here is about 1333. Okay, and this is the coexistence state. So remember, with that steady state problem, the whole goal was to show that we had a positive steady state. Okay, so I have chosen all of my parameters in such a way that I can guarantee that, in fact, I do have a positive coexistence state. So if we go back to that original problem, we could say, if you set your problem up with this exact biomass, well, your trees aren't going to compete for each other. They're not going to kill each other off. You're going to get a nice, stable forest. But the question is, what happens if I don't start at exactly these equilibrium values? If I want to start close to them, right? Maybe I start with like 9,000 hardwoods and 1,500 softwoods or something like that, right? Well, am I going to fall into this nice stable equilibrium? Or, am I going to get pushed away and maybe one of those trees is going to go extinct? Because it's very uncommon. It's very rare for me to be able to set the system up perfectly at equilibrium. What I would like is to have a little bit of wiggle room. Well, in this case, you are going to compute the Jacobians here, okay? So if you call this whole thing F1 of H and S, and you call this whole thing F2 of H and S, you got some Jacobians to compute. So the Jacobian, in this case, I need a derivative of F1 with respect to H. In this case, it is 20,000 minus S divided by 20,000. And then subtracting off H over 50,000. So the numbers aren't pretty, but I think that you're probably used to these kind of ugly numbers by now, especially if you've been doing a lot of optimization leading up to this. This is minus H over 20,000. This is minus, okay, so the second partial derivative with respect to H, this gives me minus S over 48,000. And finally, the last partial derivative, minus H over 48,000. And then minus S over 12,000. Plus 1/4. Okay, so the numbers, the numbers are the numbers, but a calculator can handle them. There's no big deal. So in this case, my Jacobian matrix, so let's call it df of H naught S naught. This thing is equal to, so it actually simplifies quite nicely. minus 7 over 75, depending on maybe your definition of nicely, minus 7 over 150, minus 1 over 36, and minus 1 over 18. And in particular, eigenvalues in this case are given by lambda is equal to minus 67 plus or minus the square root of 1339 divided by 900. You can actually just throw that into a calculator. You can very easily check that both of those are negative. Okay, so based on what I just said right over here, since both of the eigenvalues of the Jacobian are negative, that means that this coexistence state is stable, right? It says that if I start with a population of hardwood and softwood trees that is close, relatively close to this coexistence state, then I am going to fall into it. You could actually do better than this, right? And you could draw a phase plane diagram and you could really see all of those arrows sort of pointing you inwards and that sort of sucking in, right? This is more of an analytic justification for what we did already with the blue whales, right? We took the blue whale phase plane diagram and we saw all those arrows sort of pushing us into that coexistence state. If you did the phase line diagram, you'd see exactly the same thing for this hardwood problem. And it's all backed up with real mathematical theorems that tell us that since these eigenvalues are negative, then we are going to converge into that steady state, that coexistence state. Okay, we can use this idea of stability to perform a sensitivity analysis. Remember, sensitivity is measuring robustness of the system. It's asking you, even if I didn't set it up perfectly, which you couldn't have. You don't have complete information no matter what you're doing in mathematical modeling. So even if you didn't put it together perfectly, is it still going to give you approximately correct results, right? Does it allow for wiggle room? Is there a little robustness, right? If I didn't perfectly compute the effect of drag on my goggles falling, am I still going to get mostly the same ideas here, right? Is that I'm still going to fall to the ground? It's still going to take around the same amount of time? This is what sensitivity is really asking us. So we could look back at our problem, our tree problem here, and we could perform a little bit of a sensitivity analysis. So in fact, remember that we made this assumption. We said that both of them are equal to this, right? This was an assumption that we made. We said B1 is half of A1 and B2 is half of A2. So let's actually perform a sensitivity analysis around this. So let's set each of the BI's equal to a fraction, we'll call it T, times AI, okay? Now, in order to satisfy, so remember we have these two constraints that we wanted in order to discuss a coexistence state. So the first one was that BI is less than AI, right? Competition with yourself is greater than competition with the other. And remember, we talked about this predation. So this was Ri over AI is less than Rj over Bj. So in this case, I'm using I to be 1 or 2, and then j is the opposite one, right? So there's a lot of conditions here, but I don't want to write them all down. Essentially, to satisfy this, I have to have t between 0 and 0.6, okay? So I can ask myself, what happens if I vary t around these values, right? This fractional amount of predation from the other based on what you currently have, okay? So clearly, my 0.5 is well in the middle of this. So I can ask myself, if this wasn't a perfect assumption, maybe it was, actually the predation rate was 0.4 or a little bit of wiggle room, am I still going to get a stable system? Am I still going to fall into the coexistence state? Because remember, that's the only thing that I cared about. Do I have coexistence? Is it possible for both hardwoods and softwoods to exist simultaneously in this forest without one of them driving the other to extinction. Okay, well, now the equilibrium point is going to depend on the value of t, okay? So I'm going to call it h naught again. In this case, it's 10,000 minus 6,000 t divided by 1 minus t squared. Okay, so again, everything depends on t. And if you want to, you can put t equal to 0.5 in here to recover the results from the previous board. And then here we have 6,000 minus 10,000 t. And then divided by 1 minus t squared. Okay, so similarly, we've got a right-hand side that we need to linearize around, right? So again, let me just remind you, I'll call it f1 of h comma s. This is what we're going to need for partial derivatives. So we have that 10% growth rate, and then we've got 10% growth rate divided by carrying capacity, h squared. And then now we have a1 times t. So this is 0.1 t divided by 10,000 at h times s. And similarly, we have for the softwood trees, they have a 25% growth rate, and then you have growth rate divided by the carrying capacity, 6,000, and this becomes s squared. And now you have the predation, or sorry, the b terms becomes 0.25 times t, the fraction, divided by 6,000 h times s. So now what you're going to do is you're going to repeat the process, right? It's going to take a little bit of work. You're essentially going to have to find, partial derivatives of these things. They're going to include t. It's going to be a pain, but if you want, you can throw it into a computer. You can let it do the work for you. And you're going to evaluate those things at these values right here, h0 and s0. So the Jacobian in this case, the Jacobian gives me df h naught s naught, which I will just write it out for you just so you can take a look at it. So after simplifying, 5 minus 3t divided by 50 times t squared minus 1. So that's just the first component, right? And then t times 5 minus 3t. And in this case, it's 50 times t squared minus 1. Okay, so they're ugly, they're t dependent, but that's okay, right? And then I get t times 3 minus 5t divided by 12 times t squared minus 1. And then finally, 3 minus 5t times 12 times t squared minus 1. Okay, so it's an ugly matrix, right? Especially because t can take any value between 0 and 0.6. This is sometimes called a parameterized matrix, right? It depends on a parameter, in my case, this fraction t. But, it's nothing too hard. This is nothing beyond the computational power of really, really simple to use products, right? Sort of Maple, Mathematica, MATLAB, right? They can all compute the eigenvalues of this thing, and they can spit out, all kinds of information. In particular, we find that for all 0 less than t less than 0.6, both eigenvalues, there's two of them, of this matrix, h0, s0, are negative. Right, so you can go ahead and plot that for yourself, right? Use t as a symbolic variable, compute the eigenvalues. It's going to be an ugly function, but you can compute it. You can see that no matter what the value of t, as long as it's in this sort of feasible range right here, always returns negative eigenvalues. Why is this important? Well, this is the robustness that I was dreaming about, right? This tells me that, even if I get my competition with the other species off, even by a lot potentially, right? Maybe it's 0.001, really, really small. I still get a coexistence state that is stable. It gives me wiggle room, right? It gives me robustness of my model. It's telling me I don't have to have a perfect model. I have a lot of wiggle room, and I still get a stable coexistence state. So I still see that in the vector field, everything pointing in towards my coexistence, right? That tells me that not only is it possible to set up the system so that neither one of the tree species die out, but I have, a lot of room to move around. I can, be off with my initial setting up of this forest, and those trees are going to sort of negotiate with each other and work together so that they can live in this stable coexistence. This is a version of sensitivity analysis when we talk about differential equations, right? It's more related to the original ideas of sensitivity in terms of robustness. Can I get the model wrong and still get the right answer, or still get, what I was hoping to get out of this, right? And this is, again, all going back to the idea that we have imperfect information, and therefore we have to sort of know what happens if we wiggle things around, and if we start moving things and tweaking them and changing them. And in our case, we get this beautiful result that we always have a stable coexistence state. Okay, when we come back in the next video, we're going to start talking a little bit more about discrete time systems and seeing the same kind of analog where we have these eigenvalue methods, these local linearization techniques, and how we can use linear dynamics to inform us there as well.